Hi, and welcome to InterSystems Virtual Summit 2021. Databases are for storing data. They use a broad range of techniques to make sure that data is stored in a consistent, reliable, and efficiently accessible way, tapping into storage infrastructure offered by hardware vendors and cloud service providers. Quality doesn't come cheap though, and we've seen that for many customers, storage is the biggest cost factor in their overall infrastructure bill. In this session, we'll take a look at how a number of recent and upcoming InterSystems IRIS features aim to reduce the storage footprint and increase convenience. Throughout the session, we'll use numeric examples taken from two real customer deployments. BioStrand is an innovative startup in the EU and uses InterSystems IRIS as the platform for its genomics analytics solution, and they deploys on AWS. They are somewhat data heavy with a total database size of around 20 terabytes, and approximately 95% of their monthly infrastructure bill is for storage alone. The second example we'll use is for a large health network in California who are running InterSystems HealthShare in the cloud, also on AWS. They have a much larger compute component, but storage still represents over half of their infrastructure bill. I'm using two examples of solutions deployed in the cloud because those make it easier to convert from terabytes to dollars. But for customers deploying to their own hardware on-premise, we've seen very similar economics. And given how they need to size and procure their hardware up front, it's even more important to take every opportunity to economize on what gets stored. With these two case studies in mind, let's take a closer look at what goes onto those disks. There are two important drivers of storage consumption for IRIS deployments: database files and journal files. Database files are the IRIS.dat files that hold the actual data managed by your database, and it's what we call data under management on the previous slide. This is obviously directly proportional to the raw data that's being ingested over time and needs to be available for database queries. We say proportional rather than equal because for structured data, you'll typically also want a few secondary indices to ensure fast data retrieval. Unstructured data is usually persisted as a stream data type, which can be either character-based or in a raw binary format. InterSystems IRIS data engine also stores routine code along with the data, but only in rare cases does this take up a significant amount of space compared to the actual data and stream data. The second important consumer of storage is journaling, which logs transactions that change the actual data. We'll talk more about these files later, but they are crucial for maintaining the consistency of your database, and their volume is proportional to the number of transactions and the data those transactions span, so usage rather than the data itself. For BioStrand's application, there aren't a lot of transactions that change the actual data. The data gets loaded in bulk through a repeatable process that is in journals, so there are hardly any journal files to store whatsoever. In the second use case, our health network, there is an enormous amount of traffic happening 24/7, with verbose standards-based messages involved in each of these. This deployment is generating tens of terabytes journal files per day, so we can't just gloss over that in our infrastructure bill. Okay, let's take a look at how IRIS can help save you on that bill. First, we'll look at how we can economize on the data under management. We'll look at unstructured and structured data. When you store data in IRIS, it is encoded into a form that suits your data model. Encoding means organizing your data elements in a way that optimizes for efficient storage and/or access, but still keeping the individual elements as is in a readable form. You can think about a CSV file, a comma-separated value, or a fixed width file format as two different encodings for tabular data. The fixed width allows for easier access using predetermined offsets for each column, and the comma-separated format is more focused on storage consumption, so two different encodings for the same data. If you are storing your data directly in globals, you control the base encoding yourself. An IRIS database block structure then further optimizes for on-disk storage. If you are using SQL or objects, for example, we'll apply a little bit of additional magic called $list upon insertion of new data. This encodes all your SQL table columns or object properties for a single row into one string-based format that is particularly efficient at storing null values. This comes on top of those lower-level optimizations at the block encoding level. We already mentioned that we often maintain an index to quickly retrieve rows based on a particular field value. This means a second copy of parts of the original data. So we need to carefully choose whether we get enough bonus for our retrieval speed to weigh up against the storage consumption that is additional and the maintenance cost as well. IRIS block encoding for globals uses a very efficient encoding for subscripts, so that can be considered an index in its own right. But next to classic indexes, InterSystems IRIS supports a smart bitmap index type that takes a lot less space than the classic ones and fits a broad set of use cases. These features are not new, and the figures we saw on the slides earlier already include the benefits of those compact representations for structured data. Next year, we'll be releasing a new storage layout for SQL tables, optional, that is taking encoding to a next level in a way that's very similar to bitmaps, and it exploits the fact that the values of a single column all have the same data type and comes with highly optimized functions to operate on thousands of column values with a single function at a time. So that's helping both storage and performance. This new encoding type will be available both for storing the primary data as well as a new index type. So more about that in a separate session at this conference. So for truly unstructured data, such as binary files or very long character strings, encoding doesn't help much, and you need to work on the data itself to save on storage. Compression will peek inside those long streams of bytes of characters and look for repeating sequences that it can add to some kind of a dictionary, storing the sequence only once and then referring to occurrences in the stream with just a short identifier. If your data has a lot of repeating sequences, such as tags in an XML document, compression can reduce the size of a stream very significantly, much more than you can see in the crude visual here. While the savings from compression can be much larger than those from encoding, there is also a cost for decompressing the data when it needs to be returned in a readable form. So that is, again, a trade-off to be made. InterSystems IRIS has offered compressed stream data types for a while already, but they're not yet that widely adopted. Given the economics of today's infrastructure, with ever cheaper compute power, we've decided to make storage the default for all streams, starting with 21.2. When a developer decides that a field is going to be stored as a stream, that has always implied that the field isn't going to be accessed that often. So by choosing a light compression algorithm, we're only adding a tiny little bit of overhead to the field's access time. At the same time, these storage savings mean that we have fewer blocks to read from disk and fewer blocks to cache in global buffers for the same stream data. HealthShare makes heavy use of streams internally, and we ran an experiment with this new default. We found that the compression reached a whopping 80%, and global reference as a measure of I/O were down by about 10%, and CPU utilization only went up about 3 to 4% for the compression decompression work. So that was a very convincing test for the benefits of this new default. We've also tested the potential benefits on other customer data types, and for example, we found compression ratios of 30 to 50% for short to medium-sized text. We found 55% for genomic data and 75% and more for XML and other document types. Here's a visualization of the observed benefits for compressing all streams by default. At the top, you can see a breakdown of structured and unstructured data, and here's what we measured in terms of compression rates and overall savings for these customers. So the numbers you see, the 6% and the 34%, are taking into account or are starting from the full database footprint. So those are very significant and actually quite cheap to implement. Not all data is created equal. In an ERP suite, the main customer table is likely very important and accessed very frequently, but a supplier notification preference table, perhaps not so much. For the orders table as well, the most recent records are crucial and likely see a lot of read and write activity, but over time this changes, and orders from 2 years ago are probably not so important anymore. In heavily regulated industries like healthcare and finance, there is often a legal requirement to keep audit records, possibly for a very long time. This is append-only data that is often even prohibited from being changed ever. And it also may not be current at all if you're not being audited. So storing it on the premium storage with SLAs that are ready for high-frequency trading is not money well spent. So in short, there is an opportunity to align the value of data with the price you pay for storing it. That is called storage tiering. InterSystems IRIS supports mapping globals and therefore tables to separate databases and physically mount those tables from different file systems. Using our new data move utility, you can even do this on a live system without interrupting service. For example, this mapping support means that you could put the customer table on your premium SAN storage and then map the audit data to an array of spinning disks. In a cloud environment, this translates to picking the right class of storage to provision, which has become incredibly easy. Let's look at a few examples of this. Here you can see the current price per month for storing 100 gigabytes of provisioned disk space for a number of different storage tiers, each with their own SLA as offered by AWS. The high variation stands out, which means that as a customer, you can choose the SLA that you need and only pay as much. For example, you could mount that customer table on and the other main tables on IO1 storage, which is optimized for IOPS, and wire the audit table to the much cheaper SC1 volume. Note also the two S3 object storage options on the left. Object storage implements an access model that works well for accessing entire files and possibly even very big files. But it's not a very good fit for the block level access around which the IRIS database file format is built. So while S3 is often described as the most economical option for storing files, you can see from this chart that there's also very economical options in block storage that offer the block storage I/O semantics that a database like IRIS needs. So let's use this knowledge to calculate the cost savings from mounting the audit data for our health network on a cheaper storage tier. So this pie chart shows the storage breakdown after applying the stream compression. So these savings are already on top of that. So SC1 costs only 20% or less than 20% of GP2, which is the tier they use for the database files today. So moving the audit data, which is almost half of their data after compressing streams, to the SC1 tier saves them about 40% on the overall total. And because this was just one or two tables, we only had to create a very small number of global mappings. So that keeps the admin burden very small. So far, we've seen how good use of encoding and compression can help limit the storage footprint of our data under management, and how mappings can implement a simple storage tiering policy that reduces the monthly storage bill significantly. Now let's look more closely at that other main component of the overall storage footprint, journal files. First, what is database journaling? Journals are your insurance policy against data trouble. Simply put, for every update to a global node, IRIS will append the record to the journal file, which has both the old value and the new value of that global node. First and foremost, this helps when an ongoing transaction needs to be aborted, because we can glean the old values from these records. Second, we'll ship the journal records to all backup mirror members so that the new values can apply there as well, so that these systems become truly a mirror of the primary database and can take over immediately should anything happen to the primary. Finally, when you need to restore from a backup, you can read the new values from journal files and therefore bring the database forward up to the last committed transaction that was captured in your journal files. So it's clear from the above that journal files are crucial for transactional consistency and that they're in the critical path for any transaction. That's why IRIS will tell you, or IRIS will actually only tell you that a transaction has committed at all if it has been durably written to disk. So that means that we always recommend our customers to use premium storage to mount their journal files on, so that it doesn't become a bottleneck. Just a little more on the file format. So we've already mentioned that it's an append-only pattern, and only a single journal file is written to at any given time. Whenever the journal file hits the configured max size limit, we'll automatically switch over to a new journal file. So the file format is optimized for fast writing and processing, so both the rolling back and the rolling forward. Therefore, we're not compressing the values that are written to a journal record, because that overhead would get in the way of our lightning fast transaction commits. So there are some operations that where we're being a little bit more economical. So remember the bitmap indices. For example, set bit operations. For those, we'll only store the updated bit value rather than the whole bitmap that is stored in the global node, because that might be a very sizable string and add up. Still, these journal files inevitably become large if your system is seeing a lot of updates, and especially so if those updates involve a lot of data. The health network customer we commented on before is generating tens of terabyte journal files per day. So clearly there's an incentive to see what we can do to reduce that footprint. So let's take a look at journal file compression and journal archiving, which are new and coming up in 22. Let's see how this works in practice. So this concept diagram shows the database and the active journal file that it's writing to, which we've mounted on our expensive premium storage location. At some point, the active journal file will reach the maximum size and journal switch occurs. So that means that our earlier file is no longer active and that further journal records are written to a new file. This is when journal compression kicks in, and the inactive journal file, which is now taking up space on our premium storage but not seeing any real activity, will start to be compressed by a daemon process. When it's done compressing, we will delete the original inactive journal file, and we've saved some room in our premium storage by only storing the compressed copy. So we've seen compression ratios of 85% for journal files, so that's a very significant win. When the compression finishes, journal archiving kicks in. The journal archiver will take the compressed journal file and copy it to an archive location of choice. Because that location is only written to once in a process that is not in any way part of a critical path, this can be cheap, but reliable storage. It can even be object storage, such as Amazon S3. So this is a continuous process, almost like a conveyor belt. As soon as another journal switch occurs, the now inactive file will start getting compressed. As soon as a file is done compressing, it will get copied to the archive location. So with journal archiving enabled, you can more aggressively purge your compressed journal files. You can either use a schedule that considers age or number of backups, as before, or purge the local copy immediately after it has been successfully copied to the archive location and there's no more open transactions in there. So the latter option is the most aggressive way to limit the storage footprint of your journal files, yet it doesn't jeopardize the ability to restore the database, as there's always the archived copies to get back to, because IRIS never purges from the archive location. So essentially, journal archiving has decoupled your purge schedule from your backup schedule, leaving you with complete freedom on when to get rid of the archived journal files. We've heard from customers who look at this as an additional reliability feature, because this long-time journal archive on cheap cloud storage like S3 or even Glacier is more fine-grained block than what you could get out of full database backups. Let's look at what this means for the journal storage needs of our health network example. We've seen journal file compression reduce 1 gigabyte journal files to just about 150 megs. So that means their average 25 terabytes a day turns into less than 4 terabytes compressed. When adding archiving, this reduces even faster. This reduces even further, as you'd only need space for a small number of compressed files that are in transit, next to the active journal file and the 1 or 2 being compressed. That will save them literally thousands of dollars per month for the premium GP2 block storage they provision today. I'll admit that this isn't rocket science. So we have customers that already have OS-level scripts that copy journal files around, but they're a little brittle in a way. So it's much more interesting, of course, to have this all be part of the InterSystems IRIS platform itself, so that there's less for you to worry about, and that we will start compressing and start archiving at the exact right time, and also make sure that we keep the files that we still need for transaction rollback or roll forward. Just a little bit on when these features are becoming available. Journal file compression is available with 21.2, which is currently in field test. Also noting that there is no need to keep the uncompressed file around for any reason at all, because we will be rolling back and forward directly from the compressed format. Journal file archiving is expected later in 2022. While these two features are independent of one another, it is obviously recommended to combine the two. So in this session, we've seen how a number of existing and new capabilities in InterSystems IRIS can be used to reduce the storage footprint of your IRIS deployment. Encoding and compression options for your data have existed for a while already, and for streams will make compression the default shortly. Journal compression and archiving takes aim at the other important consumer of premium storage and can offer very significant savings as well, saving thousands of dollars for some of our customers. If you are a HealthShare customer, please tune in to Mark Belinsky's related session on the healthcare storage footprint reduction for a deep dive on the specifics with respect to InterSystems HealthShare. We're not done yet, though, and we are investigating other opportunities for leveraging cheaper storage options and better automation and convenience that will take advantage of existing opportunities, especially in the areas of compression and storage tiering. And we're always interested to hear your experience as well. If you happen to have any questions, feel free to use the sidebar option to submit them or tune in to the live Q&A session at the end of the conference. Thanks for watching.